In the deserts of Arizona, the thermometer just hit 112 degrees. In March, a wall of air bigger than the entire western United States is pressing down on the country like a sealed lid on a hot pot. Snow vanishing in days, rivers running early, records shattering by margins scientists call impossible. If real science wrapped in real stakes is your thing, hit that subscribe button. We publish journeys like this every week. You will see a town that broke a 50-year record by lunchtime, a snowfield that disappeared in 72 hours, and a weather pattern that may already be rewriting the American summer. Stay close. We begin. It was a Friday in mid-March, and the air in Phoenix tasted like July. The pavement outside the spring training stadium was already shimmering by 10 in the morning. A Los Angeles Dodgers fan in the stands pulled a wet towel over her head. A pitcher walked off the mound between innings just to find shade. The scoreboard read 98 degrees and rising. Nobody wanted to look at the next number. By early afternoon, 4 separate weather stations across Arizona and California pushed past 112 degrees. Not only did that smash the record for the hottest March day in the continental United States, but it was only 1 degree shy of the hottest day ever recorded in the lower 48 in April. Read that again slowly. A March day that came within a single degree of the all-time April record. For the entire country, inside the National Weather Service office, forecasters stood in front of their screens in something close to silence. The map looked wrong. Not slightly wrong. A blob of deep red the size of half the country was sitting motionless over the southwest, refusing to move, refusing to break, refusing to behave like any March pattern any of them had ever studied. One Colorado state climatologist, Russ Schumacher, told a reporter that he and his colleagues usually find a precedent for whatever the atmosphere throws at them. Some old storm, some forgotten heat wave from the 1930s, something to compare it to. But that's pretty hard to find for what's about to happen in the next few days, he said. In other words, there was no map for this. Picture the heat in physical terms. Imagine an invisible dome of high pressure stretching from the Pacific coast all the way to Texas, miles thick, pushing warm air downward the way a hand presses dough flat against a counter. Air heats up as it sinks. Clouds cannot form, wind cannot escape. Every day, the sun rises on the same bowl of trapped fire, and every day the bowl gets a little hotter. In Phoenix, the asphalt cracked along the joints. Roofers were sent home before noon. Hospitals saw a surge of heat-related calls, 3 months before they normally would. A Camelback Mountain trailhead posted a closure sign because hikers were already collapsing on the rocks. And then came the moment that made meteorologists actually stop and stare. In Yuma, Arizona, a small border town near the Colorado River, the official temperature climbed to 109 degrees. A team of weather historians began checking, then rechecking, then announced what nobody wanted to admit. Yuma had just set a new national March record. The previous mark had stood since the early 1900s. It fell by a margin so large that one veteran climatologist described it as the equivalent of a baseball player hitting 79 home runs in a season. This was the start. One Friday afternoon, one state, one number. But the dome was already growing, already drifting east, already swallowing more towns, more rivers, more snowpack, more record books. By Sunday, 14 entire states would be on the list. What happens next is what scientists call the engine, the thing that built this dome in the first place, and the thing that may build the next one even bigger. The phrase sounds almost cartoonish, a dome of heat, like something out of a cheap science fiction novel. But the moment you understand the physics, the cartoon turns into something far more menacing. Imagine a kitchen pot full of soup on a stove. You drop a heavy lid on top. The steam cannot escape. The water heats faster. The whole pot becomes hotter than it should be, and stays that way long after the burner is off. Now scale that pot up to the size of half a continent. That is a heat dome. In the upper atmosphere, around 5 miles above your head, fast rivers of air called the jet stream usually snake across the country in tight, orderly waves. They move weather along. Storms come in, storms go out. Cold fronts sweep through. The system breathes. Sometimes, though, the jet stream gets tired. It buckles. A massive ridge of high pressure forms underneath one of those waves and locks itself in place. Meteorologists call this a blocking pattern. The atmosphere stops breathing in that spot. The lid drops. Underneath the lid, 3 things happen at once. First, the high pressure forces air downward. Air is a strange substance. When you compress it, it heats up. Every 1,000 feet that a parcel of air sinks, its temperature rises by roughly 5 degrees. So even ordinary spring air, when shoved down through the dome, arrives at the surface several degrees hotter than it started. Second, the sinking air dries out. Moisture cannot survive that compression. Clouds evaporate. The sky stays a hard, cloudless blue. The sun pours down without anything to soften it. Third, the surface starts to cook itself. Without clouds, the ground absorbs full solar radiation. Without rain, the soil dries out. Without moisture in the soil, there is no evaporation to cool the air. The land becomes a giant stovetop, and the dome is the lid keeping the heat in. Now layer one more piece on top. A team of researchers at the World Weather Attribution Group ran the numbers on this exact event. They found that events as warm as in March 2026 would have been virtually impossible without human-induced climate change. Not unlikely, not rare, virtually impossible. The math does not allow it on a planet that has not warmed. Why? Because a warmer atmosphere holds more water vapor. More water vapor releases more latent heat when storms form. More latent heat pumps more energy into the upper atmosphere. And more energy up there builds a stronger, taller, more stubborn ridge. In other words, the lid is getting heavier. You can almost picture it. A thicker pot lid, a hotter burner. The same soup, but cooking faster, harder, longer than the recipe was ever designed for. This is why scientists keep saying the same uncomfortable sentence over and over. Heat domes are not new. Heat domes have been happening for centuries. What is new is how often they form, how big they get, and how far outside the historical playbook they wander before they break. The March 2026 dome did not break for almost 2 weeks, and while it sat there motionless, an entire country began to crack underneath it. The first thing to crack was the snow. Here is the part that makes climate scientists lose sleep at night. A heat dome is bad enough on its own, but the truly terrifying thing about the March 2026 event was not how hot it got. It was how long the dome refused to leave. For nearly 2 weeks, the high-pressure ridge over the western United States barely budged. The jet stream, that invisible river of fast-moving air that normally pushes weather systems along like leaves on a stream, simply stalled. The leaves stopped floating. The stream went still. A meteorologist named Greg Galena at the Weather Prediction Center described it in plain language. Basically, the entire United States is going to be hot. The area of record temperatures is extremely large. That's the thing that's really bizarre. Bizarre is the key word. Forecasters live and breathe weather patterns. They have seen heat waves before. They have seen droughts before. What they had never seen was a dome of this size, in this season, sitting in one place for this long. To understand why the dome locked itself in, picture a winding river. When a river curves gently, water flows fast and clean. But when the curves become extreme, the river slows down. Sometimes a curve gets so sharp that a section of water pinches off entirely and forms a still, isolated pond, what geographers call an oxbow lake. The main river keeps flowing. The pond just sits there. In March 2026, that is exactly what the jet stream did. It curved so sharply over the western United States that a giant pocket of high pressure broke off from the main flow and parked itself over Arizona, Nevada, and California. Storms that should have crossed the country slid around it instead. Cooler air that should have moved in from the Pacific got rerouted hundreds of miles to the north. The dome was not just stuck, it was protected. The very pattern that created it also shielded it from being swept away. And here is where the planet itself began to feed the monster. A Stanford University climate scientist named Chris Field listed 5 other gigantic heat events from the past 6 years: Siberia, the Pacific Northwest, North America, South America, each one a so-called once-in-a-millennium event, each one happening within a single decade. It's really hard to even keep up with how extreme our extremes are becoming, said Climate Central's chief meteorologist Bernadette Woods-Plackey. Researchers at Columbia University and Imperial College London have a working theory for why these blocking ridges keep forming and refusing to move. The Arctic is warming faster than the rest of the planet. As the temperature gap between the pole and the equator narrows, the jet stream slows down. A slower jet stream is a wavier jet stream, and a wavier jet stream gets stuck more often. The ridge over the southwest in March was not a fluke. It was a symptom of an atmosphere that no longer behaves the way our parents' generation understood it. A symptom of a jet stream that has been knocked loose from its old rhythm. A symptom of a planet rewriting its own weather rules in real time. And while scientists argued in journals about exactly which mechanism was to blame, the dome did what domes do. It pressed down, it heated up, it waited. Underneath it, the snow was already starting to vanish. If the heat dome was the lid on the pot, the jet stream was the hand holding the lid in place. And in March 2026, that hand had a tremor. Think about how weather is supposed to work. The jet stream rips across the upper atmosphere from west to east at speeds of 200 miles per hour, sometimes faster. It is not one single river. It is a braid of fast-moving air channels that push storms across continents like cargo on a conveyor belt. A cold front in Seattle today is in Chicago in 2 days and in New York by the weekend. That is the rhythm. When the jet stream is strong and tight, the rhythm holds. Storms move, heat waves break, cold snaps end. The atmosphere mixes itself like a giant blender, smoothing out extremes. But when the jet stream weakens, something strange happens. It starts to wobble. The waves grow taller, the curves grow longer, and occasionally one of those curves swings so far north or so far south that it pinches itself off and freezes in place. Meteorologists call this a high-amplitude meridional pattern. In plain English, it means the conveyor belt has jammed. The March 2026 pattern was a textbook jam. The northern curve of the jet stream bulged up into Canada like a balloon being squeezed from below. The southern curve dropped low into the eastern United States, flooding the Carolinas and Georgia with unusually cool, wet air. And the middle of the country, where the jet stream should have been zipping along, was instead a frozen knot. Inside that knot, the air did not move. For people on the ground, this had a terrifying effect. Normally, even on a hot day, breezes carry warm air away and bring cooler air in. Nights bring relief. Storms break the heat. But under a stalled ridge, there is no breeze. There is only the same air, getting hotter every hour the sun shines on it. In Flagstaff, Arizona, the temperature climbed past the city's previous March record on a Tuesday. By Wednesday, the new record fell. By Thursday, that record fell. The dome would leave Flagstaff with 11 or 12 straight days of temperatures higher than the city's previous March record. 11 straight days. Not 11 warm days. 11 days each individually hotter than anything ever measured there in March, going back over a century of records. Imagine a small Arizona town where the previous all-time March high was 85 degrees. Now picture the thermometer hitting 91, then 93, then 95. Each day, a new record. Each day, the residents waking up to a forecast that says it will be even hotter tomorrow. There is no end in sight, because the dome is not moving, because the jet stream is not pushing it, because somewhere thousands of miles away, the Arctic is too warm and the conveyor belt has stopped. This is the cascade, a small change in one place, a massive lingering effect somewhere else. And as the heat in the dome built day by day, scientists began watching something else with growing alarm. Far up in the mountains in the Sierra Nevada and the Rockies, the snow had started to do something it should not have been doing in mid-March. It had started to disappear. Fast. Yuma sits in a corner of Arizona where 3 states meet a river and a desert. It is a small place, about 100,000 people, mostly known for lettuce farms, military training, and being one of the sunniest cities on Earth. On the afternoon of March 20th, 2026, Yuma made history. The official high temperature at the airport climbed to 109 degrees. For most of the country, that number is shocking enough on its own. For Yuma, it was something far stranger. It was the highest temperature ever recorded anywhere in the United States in the month of March. Yuma, Arizona, hit 109 degrees, a new national March record, beating a mark set in 1954 and 1902. Stop and let that timeline sink in. The previous record had stood for over a century, 2 record-setting days, one in 1902, one in 1954, both broken on the same Friday afternoon by a small farming town near the Mexican border. To understand how unusual this is, picture the long history of weather measurement in the United States. Thousands of stations, tens of millions of daily readings going back generations. To break a national monthly record, the temperature has to beat every single number ever recorded at every single station, anywhere, in that month, ever. A new state record happens often. A new national monthly record almost never does. And it did not just barely beat the old mark, it crushed it. Lettuce farmers in the Yuma Valley had been rushing to finish their harvest. Yuma grows roughly 90% of the leafy greens eaten in the United States during the winter months. The crops are timed precisely to a cool, dry window that ends in early spring. When the heat arrived 3 weeks ahead of schedule, that window slammed shut. Field workers were pulled off the rows by mid-morning. Crews started shifts at 4 in the morning just to finish before the sun became dangerous. A truck driver hauling produce out of Yuma told a local reporter the asphalt felt soft under his tires. Tire shops reported a surge in blowouts. The county opened cooling centers 2 months earlier than they had ever opened them before. And here is the detail that meteorologists kept coming back to. The dome was not just hot, it was hot at a time of year when the human body and the local infrastructure had no preparation for it. Another saving grace for people in this heat wave is that it's not as humid as it would be if the temperatures rose in the summer. The dryness probably saved lives. But it did not save the snowpack, the soil, the crops, or the records. Across the border, the situation was even more striking. In northern Mexico, climate historian Maximiliano Herrera reported something almost unbelievable. In Mexico, even May records were trashed with March records broken by as much as 14 degrees Fahrenheit, far more than July 1936, March 1907 or June 2021, May records broken in March, by 14 degrees in a country with a long hot history. Yuma was the headline, but the real story was already spreading. Like ink in water, the heat dome was bleeding outward, eastward, northward. 14 states were about to fall in a single weekend, and the country was about to see something it had not seen since the Dust Bowl. By the time the sun rose on Saturday morning, the dome was no longer a regional event. It was a national one. Weather historian Maximiliano Herrera spent that weekend tracking record-keeping stations across the country. By Sunday night, he had compiled a list that meteorologists would be quoting for weeks. 14 states had notched their hottest March day on record since the heat dome started. California, Arizona, Nevada, Kansas, New Mexico, Nebraska, Utah, South Dakota, Missouri, Iowa, Colorado, Wyoming, Minnesota, and Idaho. Look at that list closely. It is not just the desert Southwest. It stretches from the Pacific coast to the Mississippi River. It includes Minnesota, where ice fishing season normally runs into late March. It includes South Dakota, a state where snowdrifts can pile up shoulder high in spring. It includes Iowa, the heart of the Corn Belt, where farmers were watching the soil temperature with a mix of awe and dread. 14 state records in a single weekend, in a single weather event. To put this in context, breaking a single state monthly record is the kind of news that gets a paragraph in a weather almanac. Breaking 10 in a month is a generational event. Breaking 14 in 72 hours is something the records had never quite seen before. The numbers behind the numbers were even stranger. The National Center for Environmental Information registered at least 479 weather stations, breaking records for March from Wednesday through Saturday. Herrera, who analyzed a broader set of data, said the true number was likely higher. Now picture nearly 500 small flags planted on it, each one marking a town that just had its hottest March day in human memory. The flags cluster in the desert Southwest. They spread up the Rockies. They drift east across the plains. They appear in unlikely places. A small town in Iowa, a weather station in Wyoming where the previous March record had stood since the 1930s. In the Plains states, the heat caught farmers by surprise. Wheat that should have been dormant for another month began to break dormancy. Some fields started to green up almost overnight, which sounds nice until you understand the danger. A late frost in April, which is normal in places like Nebraska and Kansas, can now wipe out a crop that was tricked into growing too early. The dome did not just break records. It set up the entire growing season for chaos. In the Midwest, the warmth brought a different kind of strangeness. Ice on lakes that should have been thick enough to drive a truck across had become unsafe. Spring thaw came weeks early. Rivers swelled with sudden meltwater, and small towns along their banks scrambled to deal with flooding when they should have been shoveling snow. A weather historian named Chris Burt, author of a book about extreme weather, made a comparison that landed hard. The physical area of this heatwave likely dwarfs two other historic heatwaves, one in 2012 in the upper Midwest and Northeast, and another in 2021 in the Pacific Northwest. The only event in American history that may have been bigger, Burt said, was the Dust Bowl summer of 1936. And that one took 2 months to play out in pieces during high summer. This dome did its damage in a single ferocious sweep in March. 14 states. One weekend, a nation that suddenly looked like its own future. And just south of the border, the records were even worse. If the United States had been put through a furnace, Mexico had been thrown into a foundry. Climate historian Maximiliano Herrera spent the weekend of March 21st cross-checking weather data from stations across northern Mexico. The numbers he found were so extreme he had to verify them twice, then a third time. Then he sent them out anyway because they were correct. In small towns across Sonora and Chihuahua, the thermometer was hitting temperatures normally seen in late May. In some places, it was hitting temperatures normally seen at the peak of summer. In Mexico, even May records were trashed with March records broken by as much as 14 degrees Fahrenheit, far more than July 1936, March 1907 or June 2021. To translate that for a moment, Mexico has a long, well-documented history of heat. The country sits closer to the equator. Its deserts have produced some of the hottest readings ever measured in North America. When a Mexican climatologist says a March record was broken by more than the famous July 1936 Dust Bowl heat, that is not a small statement. That is a statement that this event surpassed events people are still studying nearly a century later. In Sonora, ranch owners reported cattle dying within days of the heat arriving. The animals had not yet shed their winter coats. Their bodies were still adapted to the cool, dry air of February. When the dome dropped onto them, they had no defense. Veterinarians describe the deaths as similar to what they normally see in early August. In Mexicali, just across the border from Yuma, the thermometer climbed to 112. Several places in Arizona and California reached 112 degrees, an unheard of high in March. The same number was repeating itself across the borderlands. 112. 112. Like a stuck record on a turntable that no one could lift the needle off. Public health officials in northern Mexico raised the same alarm their American colleagues were raising. The danger was not just the temperature, it was the timing. People had not yet acclimated. The body needs roughly 2 weeks of progressively warmer days to build tolerance to extreme heat. In a normal year, by the time July arrives, a desert resident has already lived through a slow ramp from 60-degree mornings to 90-degree mornings to 100-degree mornings. The body adjusts, sweat glands ramp up, blood vessels learn to dilate efficiently, hydration habits become automatic. In March, none of those adjustments had happened yet. People were drinking the same amount of water they had been drinking in February, wearing the same clothes, working the same outdoor schedules. The dome arrived before the body was ready, and the body paid the price. Hospital admissions for heat-related illness in Sonora climbed by an astonishing percentage in a single weekend. Not double, not triple. Roughly 10 times the normal March baseline. Pediatric wards reported cases of severe dehydration in young children. Construction sites simply shut down by midday. In some agricultural valleys, the harvest workers, mostly migrants and day laborers, faced an impossible choice: stop work and lose pay, or keep working and risk collapse. The Mexican experience was a preview, a glimpse of what acclamation failure looks like when a population gets ambushed by summer in the wrong season. American officials in Arizona, New Mexico, and Texas began studying it carefully, because the same mechanism, in slightly different clothing, was about to play out farther north. Up in the mountains, the snow had a different reaction. It did not collapse slowly. It vanished. If you fly over the Sierra Nevada in a normal mid-March, the view is almost overwhelming. Endless white peaks, frozen lakes, pine trees buried up to their lower branches. The Snowpack, the giant white reservoir that sits on top of California, is at its annual peak. Cold, stable, massive. In March 2026, the Snowpack did not look stable. It looked like it was running for its life. Beneath the dome, daytime temperatures in the Sierra climbed into the 70s, then the 80s, then, in a few high-elevation valleys, the 90s. Snowpack does not handle that gracefully. When the temperature stays above freezing for days on end, even at altitude, snow goes from a slow, predictable melt into a fast, chaotic collapse. A snow scientist watching the satellite data described it like a glass of ice cubes left in the sun. For a while, the cubes hold their shape and the water level rises slowly. Then suddenly, all at once, everything is liquid. The snowpack of the Sierra Nevada, which California depends on for nearly 30% of its summer water supply, was hitting the same breaking point 3 weeks earlier than the historical average. High temperatures were expected to accelerate snowmelt in these parts, including the mountains of Colorado, where the snowpack levels are already lowest since 1981 due to the preceding warm winter, and the Sierra Nevada region in California, where although snowfall was average, the high heat is likely to drive rapid snowmelt. In other words, the Sierra had a normal amount of snow. The dome did not care. Streams that should have been frozen began to roar. Tahoe area ski resorts that had been planning to stay open into April watched their lower runs turn to mud in 72 hours. A teenager on the slopes of Keystone, Colorado, was photographed skiing through a literal puddle, a puddle on a ski run. In March, the image went viral, partly because it was funny, mostly because it was terrifying. For California, the implications were immediate and brutal. The Sierra snowpack works as a giant natural reservoir. Snow falls in winter, sits there frozen for months, then melts slowly through the spring and early summer, feeding rivers, filling reservoirs, supplying farms and cities all the way through the dry season. When the snow melts too fast, two bad things happen at once. First, the rivers swell beyond what dams and channels can handle, sending precious water rushing past the storage points and out to sea. Second, the rivers run dry weeks earlier than usual, leaving the late summer with nothing. A snow hydrologist with the California Department of Water Resources described it as watching a year's worth of water leave in a few days. Reservoirs filled rapidly. Then, with the snow gone, there was no second wave coming behind it. Farmers in the Central Valley who depend on that slow drip of summer meltwater started doing the math. The math did not look good. Almond growers, alfalfa producers, tomato fields. Each one needs water in July and August, not in March. By the time the dome moved on, hydrologists were already warning that California's summer water situation was likely to be the worst in years. The story was nearly identical in Colorado. Mountain snow that had taken months to build up was vanishing in days. A skier interviewed at Aspen described seeing exposed rock faces in mid-March that he had never seen before any year in late April. The dome was not just breaking temperature records, it was draining the West's water savings account in real time, right in front of the cameras. And one state was already reporting numbers no one had seen in nearly half a century. Colorado is supposed to be a state where snow is a given, where ski towns plan their seasons around reliable powder, where the Continental Divide holds enough frozen water to feed 7 downstream states all summer long. In March 2026, that promise broke. The numbers came in from the snow telemetry stations, scattered across the Rockies. Each station is a small automated outpost that measures the depth and water content of the snow on the ground. Together they form a picture of how much frozen water the state is sitting on. The picture in March was bleak. The mountains of Colorado, where the snowpack levels are already lowest since 1981 due to the preceding warm winter, lowest in 45 years, half a lifetime, a measurement that had not been seen since the era when ski lifts were powered by mechanical drives older than the people now running the resorts. The reason was layered. The winter of 2025 into 2026 had been unusually warm and dry across the Rockies. Snowstorms that should have dropped 2 feet dropped 6 inches. Ridges that should have been buried in white were showing bare rock by February. And then, before the snowpack even had a chance to recover, the heat dome arrived and finished the job. Russ Schumacher, the Colorado state climatologist, described the situation in a tone meteorologists usually reserve for hurricanes. It looks like it's just going to be record after record for warmth for this time of year falling as we get into this heat wave later this week. He was not exaggerating. By the end of the dome's stay, Colorado would log roughly 12 straight days of unprecedented March warmth. Snow that should have been gaining mass through April was instead losing it daily. Picture the Dillon Reservoir, high in the Rockies, in late March. Normally, the surrounding peaks are still wearing thick coats of snow, and the reservoir itself is half frozen. In March 2026, depleted water levels were visible at Dillon Reservoir during a season of record low snowpack as temperatures reached into the 70-degree range in Dillon, Colorado. 70 degrees in a high-altitude town where mid-March often means cross-country skiing on freshly fallen powder. Tourists who had booked spring skiing trips cancelled in droves. Local hotels watched their occupancy rates drop in real time. One inn owner told a reporter she had gone from a fully booked weekend to a third full in a single day. But the tourist losses were the smallest part of the story. The real concern was downstream. The Colorado River starts in these mountains. Its watershed feeds Las Vegas, Phoenix, Tucson, Los Angeles, San Diego, and roughly 40 million other Americans. Lake Mead and Lake Powell, the 2 giant reservoirs that hold the river's water, had been hovering at dangerously low levels for years. Each spring, the snowpack provides a refill, A bad snow year means a bad water year. A bad snow year combined with a March heat dome that incinerates whatever snow does exist means something far worse. Hydrologists ran the projections and quietly began circulating internal memos. The summer water situation across the southwest was now likely to be more constrained than at any point in the modern record, not slightly worse than last year, substantially worse. For people in the cities downstream, the consequences would arrive on a delay. The dome would move on by April, the water bills would rise by July, the reservoir warnings would follow by August. The dominoes were already falling, miles up in the Rockies, weeks before anyone in the desert cities would feel them. And every one of those falling dominoes pointed in the same direction, toward a chain reaction the West has feared for decades. Here is the brutal logic that climate scientists keep trying to explain to the public. A heat dome in March is not just a March problem. A heat dome in March is a July problem, an August problem, a September problem, a November problem. The reason is the chain reaction. Step 1. The dome melts the snowpack early. Rivers run high in March and April instead of June and July. Step 2. Reservoirs fill faster than usual, but stop filling sooner than usual. Once the snow is gone, there is nothing left to feed the rivers. The peak runoff window ends weeks ahead of schedule. Step 3. The mountain soil, which would normally stay damp from melting snow until summer, dries out by May. Trees and grasses begin to stress in late spring instead of late summer. Step 4. By the time real summer arrives, the entire western landscape is already in late-season drought condition. Rivers are low, soil is dry, plants are stressed. The fire fuel is ready months ahead of fire season. Step 5. A single lightning strike or a single sparking power line becomes catastrophic in a way it would not have been in a normal year. Fires that should have stayed small grow into infernos. Exceptional heat and near-record low snowpack are increasing risks heading into summer, including ecosystem stress and early wildfires. This is the cascade, one event in March writing the script for a disaster 6 months later. A retired federal emergency manager named Craig Fugate described the broader pattern in a quote that should be on the wall of every city planning department in America. We were operating outside the historical playbook more and more. Flood maps, surge models, heat records, events kept showing up outside the envelope we built systems around. The envelope is the assumption. The assumption is that the past 100 years of weather is a reasonable guide to the next 100. The envelope is breaking. For California, the cascade was already running. By the time the dome dissipated in early April, the state's water managers were privately warning that summer water restrictions were likely to be the most severe in a generation. Irrigation districts in the Central Valley began notifying farmers that allocations would be cut. Some almond growers started doing the calculation that no almond grower wants to do. How many trees do I rip out this summer to keep the rest alive? For Arizona, the cascade meant Lake Mead. The lake, the largest reservoir in the country, had been stabilizing slightly after years of decline. The early melt and weak inflow numbers from the Colorado River meant that stabilization was likely to reverse. Las Vegas, which depends on Lake Mead for 90% of its drinking water, began updating its conservation messaging. Phoenix issued similar advisories. For Oregon and Washington, the cascade meant fire. Forest Service officials, looking at moisture levels in the duff layer, began publicly warning that fire season was likely to start in May rather than late June. Fire crews that normally have weeks to prepare suddenly had days. And for the entire western United States, the cascade meant something deeper. It meant that the calendar everyone had been using for a century was now wrong. Spring was no longer spring in the old sense. Summer was no longer summer. The seasons were sliding sideways, and every system built around the old timing was creaking under the strain. A senior climate researcher described the moment in a sentence that became widely shared. The atmosphere is doing what physics dictates. The physics just hits different on a warmer planet. What does that mean in practice? It means a March heatwave can do what only a July heatwave used to do. It means a single weather event can rewrite a year of plans for 100 million people. And the comparisons people kept reaching for, the comparisons to the worst summers in American history, were starting to fall short. Whenever a heatwave gets large enough, weather historians start reaching for the same reference point, the Dust Bowl. Specifically, the summer of 1936, the hottest single season ever recorded across most of the central United States. For nearly 90 years, the 1936 summer has been the benchmark, the standard against which all other heat waves are measured. Wheat fields cooked into dust, railroad tracks bent in the sun, birds dropping out of the sky over Iowa. It was a slow, grinding catastrophe that lasted weeks. And in the agricultural districts of the plains, it killed thousands. When the March 2026 dome reached its peak, the comparisons started flying. Weather historian Chris Burt, who has spent his career documenting extreme weather events, walked through the comparison carefully. He gave the Dust Bowl summer its due. He noted that the temperatures in 1936 were higher in absolute terms, in part because they fell in July when the sun is at its strongest. He noted that the human toll was almost certainly worse, in part because air conditioning barely existed and rural populations had no escape. Then he made the observation that meteorologists have been quoting ever since. It may not be as large as the Dust Bowl heatwaves of 1936, but that was a series of heatwaves over 2 months during summer, not a single big event like now. The Dust Bowl summer was not one event. It was a chain of brutal heatwaves, each one breaking down before another started, spread across 2 full months. Weather historians have reconstructed it carefully. Temperatures spiked, then fell, then spiked again. Storms intervened. Some regions got brief reprieves while others cooked. The March 2026 dome was the opposite, a single, gigantic, motionless event. One coherent dome of high pressure, sitting over the western half of the country, refusing to break apart, refusing to give anyone underneath it a single afternoon of relief. Picture 2 photographs side by side. The first photograph shows a series of bonfires each, one burning for a few days, flickering across a landscape over 2 months. The second photograph shows a single wildfire stretching across an entire region, burning continuously for 2 weeks. Different shapes, different durations, different beasts. The other major difference was geography. The Dust Bowl heatwaves concentrated their worst on the Central Plains. The March 2026 dome covered the western half of the country. Climate Shift Index Level 5 alone covered approximately 3 million square kilometers, or about 29% of the continental United States, highlighting the exceptional scale of this event. 29% of the continental United States under the highest possible climate signal, all at once. This is what scientists mean when they say the dome was a record-shattering event, not just a record-breaking one. A record-breaking event nudges the old number by a small margin. A record-shattering event obliterates the old number by a margin so large that statisticians have to update their formulas. The dome did the latter. There was one other comparison floating around weather circles, the June 2021 heat dome over the Pacific Northwest. That event killed hundreds. It pushed temperatures in British Columbia higher than the all-time record in Death Valley. It is widely considered one of the most extreme weather events of the 21st century. But even that event was smaller in area than the March 2026 dome. The 2021 Pacific Northwest dome was hotter at its core, but the March 2026 dome was wider, longer-lived, and earlier in the season than its predecessor. Colin McCarthy of UC Davis called the March 2026 event the most extraordinary United States heatwave since the 2021 Pacific Northwest heat dome, 2 of the most extreme weather events in modern American history, 5 years apart, both built by the same physical mechanism, both record-shattering. The pattern was no longer a pattern, it was becoming a category, and the index that tracked it was already at its maximum. There is a tool that climate scientists use to translate weather events into a single simple number. It is called the Climate Shift Index, and most people have never heard of it. It works like this. For any given temperature on any given day in any given place, the index estimates how much more likely that temperature has become because of human-caused warming. If the temperature is 1.5 times more likely now than in a pre-industrial climate, the index reads 1. 2 times more likely, the index reads 2. 5 times more likely, the index reads 5. 5 is the maximum. 5 means human-caused warming has at least quintupled the odds of that temperature occurring on that day in that location. 5 means the climate signal is so strong that statistically, the event would be vanishingly rare without it. 5 is, in the language of attribution science, the closest thing scientists have to a smoking gun. In March 2026, the Climate Shift Index lit up the western half of the country. In 5, Climate Shift Index levels of 5, the highest possible, were forecast across the western United States from March 24th through 27th, meaning human-caused climate change made this extreme heat at least 5 times more likely. This signals an exceptional climate-influenced event. Take a moment to really absorb that sentence. The dome was not a 5% climate signal, not a 50% climate signal. The dome was a 500% climate signal, sustained over thousands of square miles, for days on end. For the people who study climate attribution, this was the moment the discussion ended. There is a long-running debate in climate science about how to talk about individual weather events. Conservative voices used to say that no single weather event can be attributed to climate change. Bolder voices have said for years that some events are now so far outside the historical envelope that calling them anything else would be statistical malpractice. The Climate Shift Index was developed precisely to settle these arguments. 5 was as definitive as the science gets. A research meteorologist at the Scripps Institution of Oceanography, Alexander Gershonov, was one of the climate scientists who began doing media interviews to explain the meaning of those numbers. The general public, he and his colleagues argued, often hears that a heat wave was made more likely by climate change and dismisses it as one of many factors. A 5 rating means it is not one of many factors. It is the dominant factor. Without warming, the event almost certainly does not happen at this intensity. The World Weather Attribution Group, an international team that runs rapid analyses of extreme weather events, ran the same exercise on the March dome. Their conclusion was even sharper. Events as warm as in March 2026 would have been virtually impossible without human-induced climate change. Virtually impossible, not unlikely, not rare, mathematically not allowed in a stable climate system. For people on the ground, this meant something direct. The discomfort of 110 degrees in March was not a freak natural occurrence. It was a forced outcome. A weather event made not just possible, but inevitable by the cumulative emissions of the past century and a half. For people in the future, it meant something more chilling. If a warming of roughly 1.33 degrees Celsius can produce a March dome of this magnitude, what happens at 2 degrees? At 3, the atmosphere has already given a partial answer. Each new dome since 2021 has been larger, longer, or earlier than the one before it. The trajectory is not flat, it is steepening. And the next thing the index measured was the size, the sheer geographical reach of the signal. 3 million square kilometers, all under maximum warning. It is hard to picture 3 million square kilometers. Try this. Imagine a rectangle drawn on a map of the United States. The western edge runs along the Pacific coast. The eastern edge cuts through Texas and the plains. The northern edge nicks the Canadian border. The southern edge crosses well into Mexico. Now color that entire rectangle in deep red. That was the area under maximum climate signal in late March 2026. On March 20th, Climate Shift Index 3, 4, and 5 all reached their largest United States extent on record since 1970. CSI 5 alone covered approximately 3 million square kilometers, or about 29% of the continental United States. 29% of the country under the highest possible climate attribution rating. Simultaneously, Climate Central, the research and communication group that maintains the index, describes a CSI of 5 as representing exceptional climate influence. The previous record extent, set during a heatwave a few years earlier, had been roughly 2 million square kilometers. The March 2026 dome blew past that by 50%. For the researchers watching the data, the geographic spread was almost more shocking than the temperatures themselves. A single hot day in a single state can be measured. A regional heatwave is large. A continental-scale climate signal at maximum strength is something that only happens when the entire atmosphere, over half a country, has been pushed into a regime that rarely existed before industrial emissions. The climate scientist Bernadette Woods-Plackey, who has been tracking these events for years, gave a quote that became almost a refrain in interviews about the dome. "It's really hard to even keep up with how extreme our extremes are becoming." She was not exaggerating. The team at Climate Central had built infrastructure to handle big heat events. The infrastructure was, by mid-March, struggling to handle the scale of what was happening. Maps that had been designed to show a few hundred record-breaking stations were instead showing more than 1,000. Between March 16th and 23rd, over 1,500 daily record high temperatures were set across the United States. Of those, 660 were also all-time March heat records, 209 of which were set Saturday, March 21st alone, 1,500 daily records in a week, 209 all-time monthly records on a single Saturday. For perspective, the National Weather Service typically logs a few dozen daily records on a normal hot day. A few hundred records in a week is considered an unusual event. 1,500 in 7 days is a category unto itself. The geographic reach also explained why the dome was so disruptive. A heat wave that affects a single region can be managed. Cooling centers open. Power grids elsewhere can send help to the affected area. Hospitals can transfer patients. The country has built infrastructure to handle localized extremes. A heat wave that affects nearly a third of the country at the same time has nowhere to send for help. The grid in Arizona is straining. So is the grid in Colorado. So is the grid in Iowa. There is no cooler neighbor to lean on. There is no spare capacity to redirect. Every system is dealing with its own version of the same crisis at the same time. This is a structural problem with extreme heat that very few people outside of emergency management discuss. Heat domes do not just break records, they break the assumption that disasters are localized. The Dome of March 2026 was a national event. It treated the Western United States not as a collection of states, but as a single interconnected system being pushed to its limits. And as the records piled up, climate scientists kept quietly making the same comparison. 5 years earlier, in the Pacific Northwest, the planet had given the world a warning that nobody quite listened to. To understand why scientists watched the March 2026 dome with such dread, you have to understand what happened in late June 2021. For most of that summer, the Pacific Northwest had been experiencing a fairly normal year. Seattle and Portland are famous for mild temperatures, cool nights, and the kind of overcast weather that has built an entire coffee culture. Air conditioning is rare in homes. Many older buildings do not have it at all. The climate, historically, simply did not require it. Then, in the last week of June, a heat dome dropped onto the region. The temperatures it produced were so extreme they shattered the imagination of everyone who saw them. Lytton, a small town in British Columbia, hit 121 degrees. The Pacific Northwest event occurred later in the year, in June, with temperatures of up to 120 degrees Fahrenheit causing hundreds of fatalities. 120 degrees in a country famous for its temperate forests. The town of Lytton itself burned to the ground the day after setting the record. The fire was triggered, in part, by a single spark in a landscape that had been baked dry by the dome. Across Oregon, Washington, and British Columbia, the death toll climbed for weeks. Final estimates ranged into the high hundreds. Most of the dead were elderly people in homes without air conditioning, people whose bodies had spent decades adapted to a cool, grey climate that had simply ceased to exist for a few brutal days. The 2021 event became a turning point in climate science. Researchers studying the dome noticed something disturbing. The temperatures it produced were so far outside the historical range that standard statistical models could barely place them on the curve. One scientist described it as if a high jumper had cleared a bar a foot above the previous world record. That is not how statistical extremes are supposed to work. A working theory emerged. The dome had been amplified by a feedback that climate scientists had hypothesized, but rarely measured directly. As the planet warmed, the increased moisture in the atmosphere provided additional latent heat to the storms that build the ridges of high pressure. More energy in the upper atmosphere meant taller, more stubborn ridges. Taller ridges meant hotter domes. A warmer atmosphere holds more moisture. More water vapor is available for latent heat release in the cyclones driving ridge amplification. In other words, the warming itself was building the structure that produced the heat, a self-reinforcing loop. For 5 years after the 2021 event, climate scientists watched the atmosphere carefully. They were waiting to see if the Pacific Northwest Dome had been a one-off anomaly, a freak alignment of conditions that would not repeat for decades, or if it was the first member of a new category. The March 2026 Dome answered the question. The same mechanism, the same kind of high-amplitude ridge, the same record-shattering temperatures. The same impossible without warming attribution finding, the only differences were the season, the geography, and the size. The March 2026 event was bigger. For the climate community, this was the confirmation they had hoped not to receive. 2 record-shattering domes in 5 years, both in North America, both built by the same physics, was no longer a coincidence. It was a pattern, a trend, a signal from a planet whose atmosphere is reorganizing itself around new equilibria. A team of researchers led by scientists at Columbia University began circulating drafts of a study examining whether the same atmospheric setup, the high-amplitude blocking ridge, was now a more common feature of North American weather. The early answers were not reassuring. And the worst part of the answer was hidden in something most people never think about: the amount of water in the air, the thing that turns a regular ridge into a monster. The most counterintuitive thing about a heat dome is that water makes it worse. This sounds wrong. Water is supposed to cool things down. We sweat to cool off. We pour water on fires. We use evaporative coolers in the desert. How can water make a heat wave hotter? The answer lies in a quirky law of physics called the Clausius-Clapeyron relation. The law states that for every degree Celsius of warming, the atmosphere can hold about 7% more water vapor. Earth has warmed roughly 1 1/3 degrees since the late 1800s, which means today's atmosphere holds nearly 10% more water than the atmosphere of our great-great-grandparents. That extra water has to go somewhere, and when it gets sucked up into a storm, it does something dangerous. To understand the mechanism, picture a rising column of warm, moist air. As the column rises, the water vapor inside it condenses back into liquid droplets. This condensation releases energy. A lot of energy. The same energy the water originally absorbed when it evaporated off the ocean, now released back into the surrounding air. Meteorologists call this latent heat release. The more water vapor in the column, the more latent heat released. The more latent heat released, the warmer the air at the top of the storm. The warmer the air at the top, the more upward push. The more upward push, the taller the ridge of high pressure that forms downstream. Now stack that effect across 100 storms over the course of a winter. Each one a little wetter than its historical counterpart, each one releasing a little more latent heat, each one helping to build a little more ridge amplitude in the upper atmosphere. By the time spring arrives, the atmosphere is loaded. The jet stream has been knocked into a wavier pattern by the cumulative effect of all those amplified storms. A high-amplitude ridge forms more easily, and once it forms, the same moisture-amplified mechanism keeps it strong, while it sits over one place. Researchers studying the 2021 Pacific Northwest event documented this loop in detail. A study by Bartosek and colleagues observed that increased atmospheric water vapor from warming likely enhances the diabatic processes that build ridges. Increased moisture content may influence the strength and development of blocking highs. In plain English, the warming is not just making heat waves hotter at the surface, it is helping to build the heat domes themselves. The lid of the pot is heavier because the kitchen is wetter. For the March 2026 dome, this had a specific implication. The winter that preceded the event had been unusually warm across most of the western United States. Pacific storms that crossed the west coast had been wetter and more energetic than historical averages. Each one had contributed a small amount of additional ridge building to the upper atmosphere. By mid-March, the atmosphere over North America was primed. When the trigger event came, a particular alignment of tropical and polar air masses, the ridge that formed was not the modest ridge of a typical March pattern. It was a giant, moisture-amplified, climate-loaded structure. It built taller, locked in harder, and lasted longer than any historical analog. The implication for the future is sobering. As the planet continues to warm, the moisture supply in the atmosphere will continue to increase. The ridges that form will continue to be amplified by that moisture. The heat domes that result will continue to push past historical envelopes. A senior researcher captured the new understanding in a single sentence that has been circulating in climate circles ever since. In a warming climate, we should expect not just more frequent extremes, but record-shattering extremes. Events that break previous records by much larger margins than historical experience would suggest. Larger margins, not slightly larger, substantially larger. The kind of margins that make weather historians sit down and stare at their data. And while the climate scientists ran their numbers, the heat dome was already producing scenes that had never been seen on American sports fields. There is a ritual in American baseball called spring training. Every March, teams from across Major League Baseball gather in Arizona and Florida for a few weeks of practice and exhibition games. The Arizona schedule is called the Cactus League. It runs through cool, dry March mornings, with games played in the kind of weather that is the entire point of the desert in early spring. In March 2026, the Cactus League ran into the heat dome. On the afternoon of March 18th, the Los Angeles Dodgers were playing the San Francisco Giants at a stadium in Phoenix. The official temperature climbed past 100 degrees by mid-afternoon. By the seventh inning, players were visibly struggling. Outfielders walked back to the dugout slowly between innings. Pitchers were rotated out earlier than expected. Baseball fans watched the Los Angeles Dodgers play the San Francisco Giants, with the heat forcing the game to end early on Wednesday, March 18th, 2026, in Phoenix. A spring training game was called early because of heat in March. For longtime followers of the Cactus League, this was unprecedented. Spring training games are sometimes called for rain, occasionally for unusual cold. The heat-shortened game in March 2026 was a first. The scenes around the stadium told the larger story. Fans wrapped themselves in wet towels. Concession stands ran out of bottled water by the third inning. A photographer captured an image of a Dodgers fan shielding herself with a rolled towel in a sun-blasted seat. An image that ran in newspapers around the country and became one of the visual signatures of the dome. A Los Angeles Dodgers fan covered up from the hot sun during a spring training baseball game against the Athletics on March 21st, 2026, in Phoenix, Arizona. The image was simple: a young woman, eyes shut, towel over her head, sun pouring down. But it captured something important. This was supposed to be a March afternoon in Arizona. People had bought tickets weeks in advance, expecting the kind of mild desert weather that has drawn baseball to Phoenix for nearly a century. Instead, they got July. Across the league, teams began making adjustments. Practice schedules shifted earlier. Some morning workouts started before dawn. Trainers issued urgent reminders about hydration to players who, like everyone else in the region, had not yet acclimated to extreme heat. A pitching coach told a reporter that he had never seen his players sweating like this in March in 20 years of coaching. The injury risk was real. Heat exhaustion in young, fit athletes is rare in cool weather. It becomes common when the heat catches a body that is still mentally and physically operating in winter mode. Cardiac stress increases. Muscle cramps multiply. Recovery times extend. The Dodgers' team doctors, who had spent decades managing summer heat in Los Angeles, found themselves doing March consultations they had never done before. It was not just baseball. Camelback Mountain, one of the most popular hiking destinations in Phoenix, posted a closure sign on its main trailhead. A sign warned hikers of trail closures due to extreme heat at Camelback Mountain on Thursday, March 19, 2026, in Phoenix. Phoenix has a famous protocol for closing hiking trails during extreme heat, but the protocol normally activates in late June, July, and August. Activating it in March was a first. The image of the closed trail head with its red warning sign became another symbol of the dome, a piece of wilderness that locals knew intimately, suddenly off-limits in a season when it should have been packed with hikers. For the people who lived in the affected cities, the spring training scenes carried a particular weight. The Dodgers in dugouts soaked with sweat, the fans hiding under towels, the trails closed. These were images of a familiar season being overwritten by a foreign one, of summer arriving in March and refusing to leave. And in the indigenous communities of southern Arizona, the same dome was producing a different kind of emergency. The Tohono O'odham Nation occupies a stretch of desert in southern Arizona that runs all the way to the Mexican border. It is one of the largest Native American reservations in the United States by land area, roughly the size of Connecticut. Most of it is open desert, with small communities scattered across long dry stretches of saguaro and creosote. For the people of the nation, heat is part of life. The summers are long and brutal. Local families have adapted over centuries. Houses are built for shade and airflow. Daily routines bend around the sun. Elders pass down knowledge about which plants to harvest, when to travel, and how to keep children safe through the hottest months. In March 2026, none of that helped. The Tohono O'odham Nation in southern Arizona issued an extreme heat warning after an official high temperature hit 108 degrees. 108 degrees in March. In a community where a March afternoon usually brings a high in the 70s, across the nation, the temperature spike triggered something the tribal government had never issued in March before: an official extreme heat warning. The warning was not a formality. The Tohono O'odham Nation, like many rural communities in the desert southwest, has a high population of elders living in homes without modern air conditioning. Many residents work outdoors, on cattle ranches, in agricultural fields, or in cultural and ceremonial roles that involve extended time in the sun. The combination of unexpected heat, vulnerable populations, and limited cooling infrastructure created a public health emergency in real time. A climate journalist named Mary Kathleen Wilson, who is herself a member of the nation, has been documenting climate impacts on Indigenous communities across the Southwest for years. Mary Kathleen Wilson, a Tohono O'odham climate journalist and advocate, was among those tracking the trends. What she has been documenting is sobering. Indigenous communities in the desert Southwest are on the front line of climate change in ways that rarely make national news. Their lands often sit in some of the hottest, driest areas of the country. Their economies often depend on agriculture, cattle, and traditional harvests that are particularly vulnerable to extreme heat and drought. Their housing stock is, on average, older and less well insulated than housing in nearby cities. When a March heat dome dumps 108 degrees on a nation that has not yet had a chance to set up summer cooling stations, the consequences are immediate. Elders begin to suffer in their homes. Outdoor workers face dangerous conditions weeks before they would normally need to take precautions. Sacred springs and water sources, already strained by years of drought, become further depleted by the sudden burst of heat. The nation's emergency management team activated cooling centers months ahead of schedule. Tribal health workers began checking on elders door to door in some communities. The air-conditioned community building that normally opened in May to serve as a refuge during summer heat opened in March instead. But the deeper concern was what the dome represented. Climate experts said the abnormally hot start to the year was only the beginning. For the Tohono O'odham Nation, the abnormal beginning was not just a weather event, it was a question. If March can now produce 108 degrees, what is summer going to look like? If the cooling centers are needed 3 months early, what does the rest of the year demand? A doctor working at a tribal health clinic described the situation in plain language. The community was prepared for hot summers. The community was not prepared for hot springs. The community was not prepared for the cumulative stress of a year that had no real cool season at all. The nation's experience was a microcosm of a larger reckoning happening across the desert southwest. Communities of all kinds, indigenous, urban, rural, agricultural, were being forced to confront the same uncomfortable possibility. The calendar they had inherited from their grandparents was no longer the calendar they actually lived in. And while the Tohono O'odham community fought to protect its most vulnerable, climate scientists across the country were sharpening a darker statistic. Heat is not just uncomfortable. Heat is the deadliest weather killer on Earth. Most people, asked to name the deadliest type of weather, will reach for the dramatic answers: tornadoes ripping through trailer parks, hurricanes flattening coastlines, lightning bolts splitting trees, blizzards stranding cars on highways. All wrong. The single deadliest weather phenomenon in the world, by a wide and sustained margin, is heat. Excessive heat is the top cause of weather-related deaths in the United States, as well as worldwide. Globally, almost 490,000 heat-related deaths occur each year, according to the World Health Organization. Almost 500,000 people every year, from a weather event that does not knock down houses, does not flood streets, does not produce dramatic news footage. Heat kills quietly, in apartments without air conditioning, in cars where children were forgotten, in retirement homes where the power went out, in fields where outdoor workers pushed through one too many shifts. The reason heat is so deadly comes down to a quirk of human biology. The body is essentially a furnace that runs at a precise core temperature, around 98.6 degrees Fahrenheit. Almost every system in the body, from the brain to the kidneys to the heart, is tuned to function at that temperature. A few degrees above it, and proteins begin to malfunction. Enzymes stop working properly. Cells start to die. The body's main defense is sweat. As sweat evaporates off the skin, it carries heat away. In a cool, dry environment, this works beautifully. The body can shed enormous amounts of heat through evaporation alone. A construction worker in a desert can sweat away the equivalent of several pots of boiling water over an 8-hour shift and stay perfectly fine. But the system has limits, 2 of them, specifically. The first limit is hydration. Sweat is mostly water and salt. If the body cannot replace what it loses, sweating slows down or stops entirely. The cooling system fails. Core temperature rises rapidly. This is heat stroke, and without intervention, it becomes fatal in a matter of hours. The second limit is humidity. Sweat only cools when it evaporates. In humid air, evaporation slows. In extremely humid air, sweat can sit on the skin without evaporating at all. The cooling system fails not because of dehydration, but because the air refuses to accept any more water. Climate scientists have a number for this second failure point. They call it the wet bulb temperature. When the wet bulb hits about 95 degrees Fahrenheit, the human body cannot cool itself, period. Healthy adults sitting in shade with unlimited water will die within hours. The body's cooling system has run out of physics to work with. The March 2026 dome, fortunately, did not produce wet bulb temperatures near that limit. The southwest is a dry climate. The air, even at 112 degrees, was thirsty enough to keep evaporating sweat. Another saving grace for people in this heatwave is that it's not as humid as it would be if the temperatures rose in the summer. That single fact almost certainly saved hundreds of lives. But it also revealed something uncomfortable. The same dome, transposed onto July, would have been a mass casualty event. A midsummer version of the March dome, with summer humidity in the southern and central states, would have produced wet bulb conditions that approached the human survivability limit across enormous areas. The lesson buried in the March event is the lesson scientists keep trying to deliver. The number on the thermometer is not the only thing that matters. The combination of temperature, humidity, and acclamation determines who lives and who dies. As the planet warms, that combination is shifting in ways that put more and more people in danger every year. A research meteorologist explained it bluntly in a recent paper. The body is a machine optimized for the climate of 10,000 years ago. The climate we are now generating is the climate of 40 million years ago. The mismatch is the danger. And the mismatch has a specific point at which it becomes lethal. Imagine the most fit person you know, a marathon runner, a young firefighter, a construction worker who has spent 20 summers under the desert sun. Now put that person in a sealed room with air at 96 degrees and 100% humidity. Give them shade. Give them as much cool water as they want to drink. Give them a fan if you like. Within roughly 6 hours, they will die. This is not a theoretical claim. It has been measured directly in laboratory studies. Researchers at Penn State University have run controlled experiments with healthy young volunteers, monitoring how their core temperatures respond to combinations of heat and humidity. The results are startling. The point at which the human body can no longer cool itself, the so-called wet bulb threshold, sits much lower than scientists once believed. For some people, it begins around 87 degrees in fully saturated air. The classic 95-degree limit is the absolute ceiling. Below it, healthy humans can survive with effort. At and above it, they cannot. The biology behind this is straightforward and grim. When skin gets warmer than the air around it, the body sheds heat through 3 pathways. Radiation, where heat simply emits outward, convection, where moving air carries heat away, and evaporation, where sweat changes from liquid to gas and pulls heat with it. In hot, dry air, evaporation does most of the work. The desert at 110 degrees can be survived for hours by a healthy person who stays hydrated. Because the air is desperate for moisture, every drop of sweat evaporates almost instantly, taking heat with it. In hot, humid air, evaporation breaks down. The air is already nearly saturated with water vapor. New sweat from the skin cannot evaporate because there is nowhere for it to go. It pools on the skin. It drips. The cooling pathway is closed. The body's core temperature begins to rise. At 104 degrees, the brain starts to swell. At 108, the person dies. The terrifying part of the wet bulb threshold is how invisibly it sneaks up. A person in a 105-degree room with 80% humidity does not feel 105 degrees of heat. They feel something far worse. Their thermometer reads 105, but their body experiences a temperature it cannot dump. The signal feels like exhaustion, then nausea, then confusion. By the time the danger is obvious, it is often too late. For the March 2026 dome, the wet bulb threshold was not directly threatened. The southwest in March is dry. Phoenix at 108 degrees has humidity in the single digits. The air is parched enough that even extreme heat can be survived if a person stays hydrated and out of direct sun. but scientists studying the dome made a quiet observation that should worry every American. The same atmospheric setup, transposed to a summer month with normal humidity, would cross the wet bulb threshold across enormous areas of the central and southern United States, the Mississippi Valley, the Gulf Coast, much of the Midwest. Wet bulb conditions approaching the human survivability limit have already appeared briefly in places like Iowa during recent summers, when high temperatures combined with high dew points to push the wet bulb past historical norms. A heat dome on the scale of March 2026 dropped onto July humidity in the central United States would not just break records, it would cross a threshold the human body is not built to handle. Even with air conditioning, a power failure during such an event could become a mass casualty disaster within a single afternoon. This is why climate scientists discussing the March dome kept returning to the same uncomfortable point. The event was a warning shot. The conditions that produced it are becoming more common, and the season of vulnerability is widening. The body has a failure point. The atmosphere is being pushed toward it, and the systems that protect modern Americans from heat were already buckling under the dome's weight. In the modern world, surviving extreme heat depends on one piece of infrastructure above all others: the electrical grid. Air conditioning is what turned the desert Southwest from a sparse, marginally inhabited region into a thriving zone of metropolitan growth. Phoenix, Las Vegas, Tucson, and Albuquerque all owe their existence to the assumption that when the temperature climbs, the power will flow and the cool air will keep coming. That assumption is one of the great unspoken pillars of American life. In March 2026, that pillar shook. Electrical grids are designed around predictable seasonal demand patterns. Utility planners know that air conditioning load peaks in late afternoon during summer months. They build their generating capacity, their transmission lines, and their maintenance schedules around that knowledge. Power plants that run hardest in July often go offline in March for routine repairs. So when the dome dropped 100-degree temperatures on the southwest in mid-March, several power plants were not even running. They were in the middle of scheduled maintenance windows. Crews had units torn open, equipment was on the ground. Reactivation timelines, which usually have weeks of slack, suddenly had hours. Across the region, grid operators began scrambling. Demand surged into territory normally seen only in peak summer. In Arizona, power consumption ran at levels that the grid managers had not modeled for the month. Transmission lines, which sag in the heat, reached temperatures that triggered automatic line ratings to be reduced. Less capacity could flow through the same wires. The math grew uglier by the hour. The vulnerability was not theoretical. A few years earlier, during a less extreme heat event in Texas, similar conditions had caused rolling blackouts that killed dozens of people in a single weekend. Grid operators knew exactly what could go wrong. They were counting hours, watching screens, hoping the dome would not stretch their margins past the point of failure. The other concerning factor was renewable generation. Solar power has become a major contributor to Southwest grids over the past decade. On a clear, hot day, solar panels can supply a meaningful percentage of regional demand, but solar panels lose efficiency as they heat up. At extreme temperatures, the same panels that produce 80% of their rated capacity at moderate heat may produce only 65%. The very conditions that drive demand higher also reduce supply. Wind generation has its own quirks. The atmospheric pattern that produces a heat dome, a stalled high-pressure ridge, also tends to produce light winds across much of the affected region. Wind farms that normally supply meaningful power in spring found themselves spinning slowly, contributing little. For households, the rising bills arrived almost immediately. Utility companies in Arizona and Nevada began warning customers that March electricity bills would resemble July bills. A hot summer is predicted across most of the contiguous United States in 2026, with almost no areas expected to have temperatures below the historical average for the season. The widespread heat will drive up energy demand and could lead to higher electric bills. For low-income families, this created an immediate crisis. The Federal Energy Assistance Program that helps people pay heating and cooling bills runs on annual budgets calibrated to historical norms. A cooling crisis in March, on top of a normal summer crisis later in the year, threatened to drain funds that were never designed to handle 2 cooling seasons in 1 calendar year. Beyond the bills, there was a deeper structural worry. Electrical grids in the United States are aging. Many transmission lines were built in the 1960s and 70s. Many substations are running on equipment from the 1980s. Replacing this infrastructure takes decades and trillions of dollars. A heat dome in March, before the worst of the summer load even began, exposed the gap between what the grid was built to handle and what the climate was now demanding. Engineers who used to plan for 100-year peaks were now seeing those peaks every few years. The buffer was disappearing. And while the grid groaned, another set of systems was also being pushed past their thresholds. The forests of the West were drying out months ahead of schedule. Forests, like grids, run on schedules. A normal western forest year goes something like this. Winter snowpack soaks the soil and the lower vegetation. Spring temperatures slowly climb, but the moisture in the duff layer, the mat of fallen needles, twigs and decomposing material on the forest floor stays high. Plants leaf out, grasses grow, streams run full. By June, the surface vegetation has begun to dry. By July, fire weather sets in. By August, the entire forest is at peak combustibility. By October, the rains return and the fire risk fades. The schedule is built into how the Forest Service operates. Fire crews are hired in late spring, equipment is staged in early summer, aerial tankers are repositioned in June. Lookouts climb their towers in May. In March 2026, the schedule did not match reality. The dome arrived at a moment when forests across California, Oregon, Idaho, and the Rockies should have still been wet. The duff layer should have been spongy. The smaller branches should have held moisture from the winter snows. Instead, fueled by weeks of unusual warmth and an early collapse of the snowpack, fuels were drying faster than fire scientists had ever measured for that time of year. A research forester at the United States Forest Service described it as a year that started with the conditions of late June. The fuel moisture readings being pulled from sticks and branches in the field were the kind that normally appear after a hot, dry month of early summer. They were appearing in March. This had 2 immediate implications. First, fire crews had to ramp up months ahead of normal. Hiring schedules were accelerated. Training programs that usually run in May began in late March. Federal officials began moving aerial firefighting assets from their normal off-season storage. Local fire departments in California and Colorado started running drills they would normally not run until June. Second, the fire season itself was redefined. Exceptional heat and near-record low snowpack are increasing risks heading into summer, including ecosystem stress and early wildfires. For California, this was particularly grim. The state had spent the previous decade adapting to a fire year that crept earlier each season. Mega fires that once happened in late August and September had migrated into July. The dome of March 2026 pushed the calendar even further. Fire scientists began openly discussing the possibility that California no longer has a fire season at all. It now has fire conditions year-round, with peaks rather than seasons. The cascade compounded. Dry fuels meant that any ignition source, a downed power line, a flat tire spitting sparks on a freeway shoulder, a careless campfire became a potential disaster. Insurance companies, already retreating from California, accelerated their pullback. Some homeowners in fire-prone counties received cancellation notices weeks after the dome passed, with insurers citing the early start to fire conditions as a factor. The most chilling assessment came from forestry researchers studying the duff layer in the High Sierra. They found that the moisture content in some areas had reached levels normally seen in August. In March, the forests were not just dry, they were primed. A retired federal emergency manager named Craig Fugate described the broader pattern in a quote that ran in major outlets after the dome passed. "We were operating outside the historical playbook more and more. Flood maps, surge models, heat records, events kept showing up outside the envelope we built systems around." The envelope in this case was the assumption that fire fuels stay wet through April. The dome shredded that assumption, and the consequences would not arrive in March. They would arrive in May, in June, in July, when the first sparks landed on a forest floor that had been waiting since winter. While the forests dried, another piece of the West was visibly draining. Reservoirs that had been counting on a slow, orderly snowmelt found themselves filling and emptying on a timeline no one had planned for. Some things happen so fast that you can watch them on a webcam. The major reservoirs of the West are wired up. Cameras on dams, sensors at intake points, live water level readings posted online. Anyone with a laptop and a curiosity can pull up Lake Mead or Hoover Dam or Folsom Lake and watch the water rise and fall in real time. In late March 2026, the watchers saw something unsettling. The reservoirs were filling. Fast. Almost too fast. Folsom Lake near Sacramento surged with meltwater from the Sierra Nevada. The American River, which feeds the lake, ran at flows normally seen in late spring during heavy snow years. Inflows climbed daily. Reservoir managers, doing the math, realized they had a problem most Westerners have not had in years. Too much water arriving too fast. Dam operators began releasing water downstream to maintain the safety margin in the reservoir. This is standard practice during fast inflow events. But it carries a brutal irony. Water released early cannot be saved for later. The water that should have arrived in pieces over months, replenishing the reservoir steadily, was instead arriving in a single rushing pulse. Some of it could be captured. Most of it had to be passed through. The numbers told the story. By the end of March, melt-driven inflows into California reservoirs had peaked roughly 3 weeks ahead of their historical timing. The peak was sharper, narrower, and shorter than normal. A senior hydrologist with the California Department of Water Resources described what was happening to a reporter. The state was getting all of its runoff at once. Instead of a long, useful, gradual delivery of water from the snowpack to the rivers to the reservoirs to the cities and farms, the state was getting a brief flood and then nothing. Lake Mead, the largest reservoir in the country and the lifeline for 40 million people in the desert southwest, was watching the same dynamic play out farther up its watershed. The Colorado River Basin had received a moderate winter snowpack, but the dome was now driving that snowpack into rapid melt. The reservoir would see a brief uptick from the inflows, then it would resume its long, slow decline. For the people who manage the West's water, this was a doctrine-shaking moment. The entire Western water system was built on the assumption that mountain snowpack would act as a giant slow-releasing battery. Snow falls in winter, stays frozen for months, melts gradually through spring and early summer, feeds the reservoirs steadily. The reservoirs hold water through the dry summer and fall. A heat dome that compresses the snowmelt into a few weeks breaks the battery. The water still arrives, but not in a useful form. A reservoir that fills in March and stays full through summer is functional. A reservoir that fills in March, releases excess water to maintain safety, and then has nothing flowing in during May, June, and July, faces a long, stressful summer. For agriculture, the implications were immediate. Irrigation districts in California's Central Valley began revising their summer allocations downward. Farmers who had been hoping for a normal year were told to plan for a constrained one. Almond growers, citrus producers, and rice farmers all began their own mathematical exercises. How much can we plant? Which fields do we fallow? Which trees do we cut? The hydrologists also worried about the long-term picture. Each year that the snow melts earlier, the soil dries out earlier. Each year the soil dries out earlier, the next winter's snow has less moisture to soak into. Each year the snow has less moisture to soak into, the runoff becomes more flashy and less reliable. A self-reinforcing pattern where the system progressively loses its ability to store and deliver water. The webcams kept rolling. The reservoirs kept showing their changing levels. And somewhere in the data feeds, statisticians were watching another set of numbers spin past historical norms at a speed that would have been unthinkable a decade ago. Numbers can sometimes capture what words cannot. By the time the dome dissipated in early April, climate scientists had finished tallying the damage to the record books. The result was a statistical fingerprint of the event that was almost hard to comprehend. Over 7,000 daily records and roughly 2,000 monthly records fell over the course of the event. 7,000 daily records, 2,000 monthly records from a single weather event spanning roughly 2 weeks. Take a moment with those numbers. A daily record is the highest temperature ever recorded for that specific date at that specific location. A monthly record is the highest temperature ever recorded for that entire month at that location. Daily records are easier to break since only a single date is in play. Monthly records are dramatically harder since they require beating the warmest day across 30 days of history at that station. 2,000 monthly records, all in the month of March, all in the same event, is unprecedented in the modern history of American weather. The breakdown by individual states told an even more striking story. In a typical year, the entire continental United States might log a few dozen monthly heat records over the entire month of March. The dome produced more monthly records in 2 weeks than the entire country normally sets in a decade. The pace of record setting was accelerating. Between March 16th and 23rd, over 1,500 daily record high temperatures were set across the United States. Of those, 660 were also all-time March heat records, 209 of which were set Saturday, March 21st alone. 209 all-time March records on a single Saturday. Climate scientists studying long-term trends had been documenting the gradual rise in heat records for decades. The ratio of hot records to cold records had been climbing. In a stable climate, daily heat records and daily cold records should appear in roughly equal numbers over time. In a warming climate, heat records pile up faster than cold records. The United States is breaking 77% more hot weather records now than in the 1970s, and 19% more than the 2010s. 77% more. The ratio is no longer subtle. Heat records are not just edging ahead of cold records, they are dominating. The dome of March 2026 was in a sense the most concentrated expression of that long-term trend. Decades of slow warming, all delivered to the surface of the country in a single focused event. Records that had stood for 50, 80, even 100 years fell in a single afternoon. For the people maintaining these records, the workload was crushing. Volunteer cooperative observers across the country logged readings, sent them to regional offices, watched their numbers get checked, verified, and entered into the national database. Climate Central staff worked late nights compiling lists. The National Centers for Environmental Information processed station data faster than the agency had ever processed it for a March event. A weather historian named Maximiliano Herrera, working independently from his home, kept one of the most thorough running tallies. His updates, posted on social media throughout the dome, became a primary reference for journalists and climate scientists alike. Herrera does this work as a hobby. The fact that a private citizen with a spreadsheet was producing some of the fastest tallies of records anywhere in the world was, in itself, a comment on how quickly the climate was outpacing the institutional capacity to track it. A climate journalist captured the strangeness of the moment in a single line. Last month's heat was the weather equivalent of a major leaguer hitting 79 home runs, or an NFL quarterback throwing 60 touchdowns in a season. In sports terms, it was the kind of statistical anomaly that breaks the language of analysis. There is no smooth way to describe a record broken by that margin. The graphs, simply lurch. And out in the financial world, a different set of professionals was already drawing their own conclusions about what numbers like these meant. Conclusions that would show up in mortgage rates, in insurance premiums, in the very economic foundations of entire neighborhoods. There is a saying among climate scientists: the clearest signal that climate change is real is not the science, it is the insurance companies. An insurance company looks at historical data, runs the numbers, calculates the odds of a house burning, a car crashing, a storm flooding a neighborhood, and prices its policies accordingly. If the numbers show a 1 in 500-year event, the company prices in a 1 in 500-year risk, but the numbers depend on the past being a guide to the future. And in much of the western and southern United States, the past has stopped being a guide. The retired federal emergency manager Craig Fugate, who spent years running disaster response at the highest levels of government, captured the insurance industry's quiet recognition in a single sentence: "We built communities on about 100 years of past weather and assumed that was a good guide going forward." That assumption is starting to break, and the clearest signal isn't the science debate, it's insurers walking away. Insurers walking away. That is the polite phrase. The reality, in places like California, parts of Florida, and increasingly Arizona and Texas, is that major insurance companies have simply stopped writing new policies, dropped existing ones, or raised premiums to levels that price ordinary homeowners out. The math is brutal. A house in a fire-prone California county might face an annual fire risk of 1 in 200 a decade ago. The same house today, with longer fire seasons, drier fuels and more heat domes priming the landscape, faces an annual risk that is 2 or 3 or 4 times higher. An insurance policy that cost $2,000 a year suddenly needs to cost $6,000 to break even. In some cases, the math no longer works at any price the homeowner can afford. The March 2026 dome was, for the insurance industry, another data point in a steepening curve. Fire conditions arriving earlier, snowpack failing more often, drought windows widening, heat events becoming more frequent and more intense. Each event slightly nudges the actuarial tables in a direction that makes coverage more expensive. In California, the state insurance commissioner has been working for years to keep the home insurance market functional. New regulations have tried to balance the demands of insurers with the needs of homeowners, but the underlying problem cannot be regulated away. The risk is rising. The number and average cost of inflation-adjusted billion-dollar weather disasters in the last couple of years is twice as high as just 10 years ago and nearly 4 times higher than 30 years ago. Twice as high. 4 times higher than 30 years ago. The trend is not subtle. For homeowners, the consequences are immediate and sometimes devastating. A cancelled insurance policy can trigger a mortgage default, since most lenders require coverage. A community where insurance is no longer available becomes a community where homes cannot be sold or refinanced. Property values drop, tax bases erode, public services strain. Whole neighborhoods can hollow out, slowly, in the face of a risk that does not arrive as a single dramatic event, but as a steady, uninsurable creep. In Florida, similar dynamics have been playing out for years, driven by hurricane risk. In California, the driver is fire. In other parts of the country, it is flooding, hail, or heat-related infrastructure failure. The pattern is the same. The places where the climate is changing fastest are the places where private insurance retreats first. Some economists have started calling this the climate insurance crisis, though it is really an insurance climate crisis. The market is sending a price signal. The signal says that the world the insurance industry priced is no longer the world that exists. For Americans wondering whether climate change has begun to bite into ordinary life, the answer has been hiding in plain sight. It is in the cancellation letters, in the premium hikes, in the small print of mortgage agreements. The dome of March 2026 did not break that system. It just added another data point to a system that was already breaking. And the structural changes in the atmosphere that produced the dome were also rewriting something else, the way American winters work. Long before the dome made headlines in March, something stranger had been happening to American winters. A weather pattern called the warm west, cool east dipole had been showing up year after year. The western United States had been running unusually warm and dry. The eastern United States had been running unusually cold and stormy. The plains in between had been bouncing between extremes. That warm west/cool east dipole has become a recurring feature of North American winters over the past decade, and a growing body of research suggests that the winter atmospheric circulation over North America appears to have shifted, driven by greenhouse gas-forced changes in the jet stream. The dome of March 2026 was not a one-off. It was, in the words of one climate scientist, the most extreme pulse in a winter-long pattern that had locked the West into warmth and the East into cold for months. To understand the dipole, picture the jet stream as a giant, undulating ribbon flowing west to east across the continent. In a normal winter, the ribbon waves modestly. Storm systems pass through. Cold and warm spells alternate. The atmosphere does its breathing. In recent winters, the ribbon has started to lock into a recurring shape. A big northward bulge over the west pushing warm Pacific air far into Canada. A big southward dip over the east, pulling cold Arctic air down into the Carolinas and Georgia. The dip and the bulge feed each other. Once the pattern locks in, it can persist for weeks or months. For the West, the pattern means warmer winters, less snow, earlier snowmelt, drier soils heading into spring. By the time a heat dome arrives, the landscape is already primed. For the East, the pattern means colder winters. Snowstorms in places that used to get rain, frozen pipes in cities that used to escape such weather, major disruptions to infrastructure. Climate scientists have been studying why this pattern keeps recurring. Several factors appear to be at play. The Arctic has been warming faster than the rest of the planet, which weakens the temperature gradient that drives the jet stream. A weaker gradient means a weaker, wavier jet. A wavier jet locks into stuck patterns more often. There are also influences from the tropical Pacific, where ocean temperatures shape the ridges and troughs that propagate northward. Recent shifts in those tropical patterns have favored exactly the dipole configuration that has been dominating North American winters. Whatever the precise mechanism, the consequences are visible in the records. Mountain snowpack across the west has been running below average. Eastern winter storms have been hitting harder. The transitional months, like March, have been seeing exactly the kind of stuck patterns that produce events like the dome. The implications stretch beyond winter. A warm west, cool east winter shapes the spring that follows. The west enters spring with a depleted snowpack and dry soils, conditions that amplify any heat event that comes along. The east enters spring with frost-stressed crops and battered infrastructure. Each region inherits a more brittle setup than it once would have. Some climate scientists are now arguing that this dipole represents a long-term shift in North American atmospheric circulation. Not a fluctuation, not a temporary pattern, a new equilibrium that the climate is settling into as the planet warms. If they are right, the March dome is not going to be remembered as an anomaly. It is going to be remembered as a sample. The first clear glimpse of what a typical late winter looks like in the new pattern. For the people designing infrastructure, planning agriculture, managing water, and selling insurance across the western United States, this is the question that keeps surfacing. Are we still in the old climate, occasionally visited by extreme events? Or have we already crossed into the new climate? The dome of March 2026 suggested an answer. And another shift was already brewing in the Pacific Ocean, one that would push the rest of 2026 in a direction the country was not prepared for. While the dome was peaking over the western United States, ocean buoys far out in the Pacific were already telling another story. The waters along the equator, west of South America, were warming. Slowly at first, then more decisively. By April, federal climate forecasters had moved their probabilities into a range that meteorologists pay close attention to. El Niño is now 85% likely by summer. El Niño is one of the most important climate patterns on Earth. When the surface waters of the eastern equatorial Pacific warm above their long-term average, the change cascades through the global atmosphere. Trade winds shift, storm tracks reroute, monsoon patterns weaken in some regions and strengthen in others, hurricane seasons get reshaped, droughts and floods migrate around the planet. For the United States, El Niño tends to produce a few signature effects. Winters often see more rain in California and the Southwest. The Pacific Northwest tends to dry out. The Gulf Coast often gets stormier. The Atlantic hurricane season is usually suppressed by stronger upper-level winds. But the summer effects are subtler. The southern United States tends to see more rainfall, potentially easing drought in parts of Texas and the Gulf Coast, while the northern United States and Pacific Northwest often get drier and warmer. For the summer of 2026, that combination was concerning. The West had just gone through a winter of warmth and drought, capped by a record-shattering heat dome in March. An El Niño summer would tend to push the Pacific Northwest, already battered by years of fire and heat, toward more dryness and warmth. The plains and Midwest, meanwhile, could see more thunderstorms and more flooding. There was another wrinkle. El Niño suppresses Atlantic hurricanes by increasing wind shear over the basin. The Colorado State University hurricane forecast for 2026 reflected this. Just 13 named storms predicted versus the 14-storm average. A quieter Atlantic season would normally be welcome news, but hurricane intensity, not just frequency, has been climbing for years. A single major hurricane in a quieter year can still cause more damage than several minor hurricanes in a busier year. The math of climate change has made the worst storms stronger, even as the number of storms moves up and down. For the broader summer outlook, the picture forming in the data was unsettling. Summer 2026 will probably be hotter than average for most of the country. NOAA's Climate Prediction Center already has 36 states leaning toward above normal temperatures this summer. 36 states, out of 48 in the contiguous United States. That is 3/4 of the country, all flagged for hotter than usual conditions. The forecasters who put together these maps are professionally cautious. They include extensive uncertainty in their language. They are not in the business of making dramatic predictions. When their maps tilt this strongly in one direction, it is a meaningful signal. For the planners and policymakers reading those maps, the question was no longer whether to prepare for heat, it was how much to prepare for. The dome of March had stretched their imagination. The summer outlook was telling them not to relax. And one specific kind of summer threat was rising in importance, a threat that combined the energy of a heat dome with the violence of a thunderstorm. Take that map again. 36 states colored in shades of pink and red, indicating elevated probability of above normal temperatures. What does it actually mean for the people who live in those states? For the desert Southwest, the answer is straightforward. Hotter summers in already hot regions, more days above 100 degrees, more nights that fail to cool below 80, more strain on power grids, hospitals, and outdoor workers. The worst of the heat will focus across parts of California, Idaho, Montana, Nevada, Oregon, Utah, Washington, and Wyoming, fueling a widespread fire threat. For the Midwest and Great Plains, the implications are different. The summer pattern often brings combinations of heat and humidity that push the heat index, the so-called feels-like temperature, into dangerous territory. The Dome of March was made survivable by the dry air of the Southwest. A similar event in July over Iowa or Nebraska or Missouri would be a different beast entirely. Humid heat does not cool at night. Indoor air conditioning is not optional. Outdoor work becomes life-threatening. For the Northeast, the forecast suggested a continuation of a trend that has been building for years. In the Northeast, temperatures are expected to be 1 to 2 degrees higher than average from June to August. and the number of 90-degree days is predicted to be near or above the historical average. A few extra 90-degree days might sound minor. It is not. Heat-related deaths in the Northeast have been climbing because the region's housing stock, especially older apartment buildings in cities like New York and Philadelphia, is poorly suited to extreme heat. Many older buildings lack central air conditioning. Many low-income residents cannot afford window units or the electricity to run them. A few extra 90-degree days, especially when combined with overnight lows that fail to drop below 80, can produce mass casualty events. For the Southeast, the forecast was less extreme but still concerning. The region tends to baseline at high heat anyway. The marginal effect of a hotter-than-normal summer is to push more days above the comfort threshold and to extend the season at both ends. The widespread nature of the forecast created a different kind of problem. A summer where most of the country is hotter than usual is a summer where there are few cool refuges. Heat waves in localized regions can be managed by sending help from cooler regions. A nationwide pattern of elevated heat strains every system everywhere. There was also the question of timing. A normal summer's heat builds gradually, people acclimate, bodies adapt. A summer that arrives as the rebound from a March heat dome is different. The cool-down period between the dome and the start of summer was short. Many people in the West never fully recovered from the March event. Their bodies entered the summer already accustomed to elevated heat. Sounds protective, but it can also mean their cooling systems started the summer already in heightened use. For utility planners, the 36-state map was a budgeting nightmare. Generation capacity, transmission infrastructure, and emergency power purchases all run on assumptions about peak demand. A summer of elevated demand across most of the country means tighter margins everywhere. The kind of safety nets that allow Texas to lean on Oklahoma or California to import from Oregon become less reliable when both the lender and the borrower are stressed. For agriculture, the implications scaled by region. Corn and soybean farmers in the Midwest face yield reductions when nighttime temperatures stay too warm. Cattle in feedlots experience heat stress that affects weight gain. Almond and citrus growers in California, already wrestling with reduced water allocations, face additional evapotranspiration losses. The summer outlook was, in essence, a delivery of the bill for the dome's preview. And while the broad pattern of heat was concerning, a more focused threat was already showing up in the forecasts for late June and July. The kind of storm that does not show up on a hurricane map. Most Americans have never heard the word derecho. Then they have one. A derecho is a long-lived line of thunderstorms that produces destructive straight-line winds across hundreds of miles. The name comes from the Spanish word for straight, distinguishing the storm from the rotating winds of a tornado. Derechos are sometimes called inland hurricanes because the wind damage they produce can rival a moderate hurricane. The difference is that derechos arrive without warning, often during heat waves, and can race across half a state in a single afternoon. The conditions that produce derechos are intimately tied to the conditions that produce heat domes: hot, humid air at the surface, a capping layer of warmer air aloft, a trigger, often along the northern edge of the dome, that breaks the cap and sends massive amounts of energy upward. Once the storms form, they organize into a long curved line that surfs along the boundary of the heat dome, drawing energy from the temperature contrast. For summer 2026, forecasters were already flagging the derecho risk. In July and August, there will be a rising risk of destructive lines of thunderstorms, known as derechos. A derecho is much more powerful than a typical thunderstorm, and is sometimes called an inland hurricane because of the widespread wind damage it can cause. Winds can exceed 100 miles per hour, strong enough to flatten cornfields and trigger power outages that last for days in the summer heat. The reason these storms are so dangerous is the combination of speed and persistence. A typical thunderstorm lasts 30 minutes and covers a few miles. A derecho can last 12 hours and travel 800 miles. On June 20th, 2025, intense thunderstorms broke out across North Dakota, spawning the first EF5 tornado in 12 years. That severe weather event also featured an intense derecho that raced across 800 miles in about 12 hours and unleashed winds up to 106 miles per hour. 800 miles in 12 hours, 106 mile per hour winds, enough to flatten cornfields, snap power lines, knock down trees, peel roofs off houses. The combination of derecho-driven outages with summer heat creates one of the worst possible scenarios for human survival. A heat dome pushes temperatures to dangerous levels. A derecho knocks out power across entire states. Air conditioning fails. Medical equipment fails. People, particularly elderly residents, find themselves trapped in homes that are heating up by the hour with no cooling system to save them. This is exactly what happened during the August 2020 derecho that swept across Iowa. Hundreds of thousands of people lost power in a region that was experiencing dangerous heat. The death toll from the combined event included people who survived the storm only to die in the subsequent heat without electricity. For summer 2026, the forecasters were warning that the El Niño pattern, combined with the energy already loaded into the central states by months of unusual warmth, made derecho conditions more likely than usual. The exact timing was unpredictable. The general elevated risk was clear. For utility companies and emergency managers in the central United States, the implication was a need for redundancy, backup power for hospitals, mutual aid agreements with neighboring states, pre-positioned tree-clearing crews. The list of preparations grows longer every year, and the budgets to fund those preparations have not always grown with it. For ordinary residents, the practical advice was the kind that climate adaptation specialists have been giving for years. Have backup power if you can. Know where the nearest cooling center is. Have a plan to check on elderly neighbors. Keep a few days of water, food, and prescriptions on hand. None of this is about doom. It is about the same kind of preparation that the country has always done for hurricanes and blizzards, now extended to a new category of compound disasters. A senior researcher described the new reality bluntly. The age of single-hazard planning is over. Heat waves, storms, droughts, fires and outages are now intersecting in patterns that the old planning models did not anticipate. And the cities themselves, the places where most Americans actually live, were beginning to show that they had been built for a climate that no longer exists. Walk through downtown Phoenix on a hot afternoon, or downtown Las Vegas, or downtown Houston, or increasingly, downtown Salt Lake City. You will notice things you might not have noticed in earlier years. Asphalt that ripples in the heat, bus stops with no shade, concrete sidewalks too hot to touch, buildings designed for summer day temperatures that the city now exceeds for weeks. American cities were built for the climate of the 20th century. The climate that produced them is no longer the climate they sit in. The mismatch shows up in dozens of small ways. Asphalt roads, which absorb solar radiation and re-radiate it as heat for hours after sunset, were laid out across vast urban areas during decades when summer afternoons rarely exceeded 100 degrees. The same asphalt now bakes through afternoons that routinely top 110. Surface temperatures on dark asphalt can exceed 150 degrees on a hot day, hot enough to burn skin within seconds. Building codes from the 1970s, 80s, and 90s did not anticipate the heat loads that current summers produce. Older houses were built with thinner insulation, smaller air conditioning systems, and roof colors that absorb rather than reflect heat. Retrofitting is expensive. Many homeowners cannot afford it. Many landlords have no incentive to do it. Public transit systems were designed assuming that riders waiting at bus stops would not be facing potentially deadly heat. Many bus stops in American cities have no shade, no shelter, and no cooling features. A passenger waiting 15 minutes for a bus on a 105-degree afternoon is exposed to conditions that can produce heat illness particularly for elderly riders and people with medical conditions. Power infrastructure runs through the same outdated assumptions. Substations designed for 1970s peak loads are running at near capacity in modern summers. Transmission lines that sag in the heat now sag a little more often, a little more dramatically, and into territory that increases the risk of contact with vegetation and wildfire ignition. Water systems carry their own legacy. Pipes laid in the early 20th century, especially in older cities like Chicago, New York, and Boston, were not designed for the freeze-thaw cycles of recent winters or the demand spikes of recent summers. Burst pipes have become more common. Water main repairs, once a routine maintenance task, have grown into a significant urban expense. The retired emergency manager Craig Fugate, in his comments after the dome, kept returning to a specific phrase: "We were operating outside the historical playbook more and more." The playbook is the assumption that yesterday's climate will be tomorrow's climate. Build for the temperatures of the past century, the playbook said. Pour the asphalt for the rains of the past century. Lay the pipes for the freezes of the past century. The new climate has invalidated the playbook, and it is doing so faster than cities can rewrite their codes. Some cities are responding. Los Angeles has begun painting some streets with reflective coatings to reduce surface temperatures. Phoenix has appointed a chief heat officer, a position that did not exist a decade ago, with a budget to plant shade trees, retrofit bus stops, and develop heat preparedness plans. Miami has begun similar work. Singapore, which faces year-round tropical heat, has been a global model for urban heat reduction. But the scale of the problem is enormous. Replacing or modifying urban infrastructure takes decades and billions of dollars. The climate is moving faster than the budgets. For ordinary residents, the urban heat island effect compounds the misery. Cities can run as much as 10 degrees hotter than the surrounding countryside, particularly at night, because all that absorbed heat has nowhere to go. A city resident who lives near a treeless intersection of asphalt streets is, for all practical purposes, living in a different climate than a neighbour a few miles away with a tree-lined yard. The dome of March 2026 exposed all of this. The unusual timing meant that systems designed for summer challenges were being tested in March. Many failed gracefully, some did not. And in the same way the cities had been built for the wrong climate, the country's flood maps had been drawn for a hydrology that no longer exists. Insurance, real estate, mortgages, and zoning all depend on a single document. The flood map. For decades, the Federal Emergency Management Agency has produced flood maps showing which areas are likely to flood in a 100-year event. A 100-year event is by definition a flood with a 1% chance of occurring in any given year. Houses in those zones are required to carry flood insurance if they have a federally backed mortgage. Houses outside those zones are not. The system has worked, more or less, for decades. The problem is that the system depends on the past being a guide to the future, and in many parts of the country that assumption has broken down. Floods that the maps say should happen once a century are now happening every few years. Houses outside the official flood zone are being inundated repeatedly. Neighborhoods that were considered safe for development are watching their streets fill with water during storms that would not have produced such effects a generation ago. The dome of March 2026 contributed to the problem in an indirect but important way. By melting snowpack rapidly and pushing reservoirs to release water early, the dome triggered downstream flooding that the maps had not anticipated for that time of year. Rivers in California that normally carry their peak flows in May and June carried them in March instead. Floodplains that were dry in March in normal years were briefly inundated. The retired emergency manager Craig Fugate, in his post-dome interviews, identified this as one of the clearest signs that the playbook was breaking. Flood maps, surge models, heat records, events kept showing up outside the envelope we built systems around. Flood maps, surge models, the very tools the country uses to plan for disasters, were systematically underestimating risk. Several factors are driving the change. A warmer atmosphere holds more moisture, which means heavier rainstorms when storms do form. A given storm can drop more water than a similar storm could have a few decades ago. Soils saturated by repeated rain events lose their absorbent capacity, sending more water rushing into rivers. Urban development paves over land that used to soak up runoff. The combined effect is that floods are getting bigger, more frequent, and more unpredictable. The maps, however, are slow to update. A single map revision can take years, requiring new hydrological studies, new modelling, public comment periods, and political navigation. For homeowners, the consequences play out in cascading misfortune. A house outside the official flood zone has no flood insurance requirement. The owner may have no idea that the house is now at meaningful risk. When a flood arrives, the damage may be uninsured. The federal disaster aid that follows, if it comes at all, often falls far short of full recovery. For developers, the outdated maps create perverse incentives. Land outside the official flood zone is cheaper to develop. New houses and apartment buildings keep rising in places that are technically outside the maps but functionally at risk. The next flood disaster is in effect being built into the landscape every year. For local governments, the political dynamics are difficult. Updating a map to expand the flood zone immediately reduces property values and increases insurance requirements for homeowners in the newly affected area. Voters do not like this. Politicians often resist the maps that scientists recommend. The result is a map system that lags reality by years or even decades. The dome of March 2026 did not create this problem. The dome simply added another data point to a long-running gap between the maps and the actual hydrology of the country. Each year the gap widens. Each year the disasters that arrive in unmapped areas grow more numerous. A senior researcher at a major university studying the flood map problem summarized the situation in a single, uncomfortable sentence. The country is making real estate and insurance decisions using maps that describe a climate that no longer exists. The same observation, applied to almost every category of climate planning in the United States, would not change. And the fundamental rhythm of summer life, the way Americans sleep through August nights, was beginning to shift in a way few people consciously noticed. Of all the changes the warming climate is producing, one of the most quietly dangerous is happening at night. Summers used to follow a familiar daily rhythm. Hot afternoons gave way to cooler evenings. Overnight temperatures dropped into ranges where bodies could recover. Houses could shed heat. Air conditioners could rest. Plants could relax their water demand. Morning broke with a crisp, almost cool feeling. The next day's heat had to build from a clean baseline. That rhythm has been breaking, and in many parts of the United States, it now breaks for weeks at a time. The phenomenon is called overnight warming, or in its most dramatic form, the tropical night, when the temperature fails to drop below 80 degrees. Climate data shows that overnight low temperatures across the United States have been rising faster than daytime highs. The reasons are several. Increased atmospheric moisture traps heat near the surface overnight. Urban heat islands, fed by absorbed solar radiation in concrete and asphalt, slowly release that heat through the dark hours. Warmer Gulf Coast and Atlantic waters mean that humid nighttime air masses carry more energy. The result is a summer that no longer cools. For the human body, this is a serious problem. Sleep is a primary mechanism by which the body recovers from heat stress. A cool night allows the cardiovascular system to relax. Core temperature drops. The kidneys catch up on fluid balance. The brain consolidates memories and clears metabolic waste. A hot night denies the body these recovery windows. Heart rate stays elevated. Sleep becomes fragmented. The body wakes up the next morning already partially cooked, with no reserve to absorb the next day's heat. For elderly residents, particularly those without air conditioning, hot nights are a primary driver of heat-related deaths. In the Pacific Northwest heat dome of 2021, many of the fatalities occurred during nights when the temperature failed to drop below the upper 70s. The bodies of the deceased simply could not catch a break. For summer 2026, forecasters were already pointing to overnight warmth as a feature of the season. A late surge of heat and higher humidity could increase temperatures during the day across the northeast, making way for warmer nights. Warmer nights. The phrase sounds almost pleasant. The reality is dangerous. In the desert southwest, overnight temperatures during the worst of the March dome refused to drop into safe ranges in many cities. Phoenix recorded multiple consecutive nights where the low remained above 80. The pattern produced the same physiological strain that summer overnight warmth produces in July, but in March, when bodies were not yet acclimated. For city planners, the overnight problem creates a unique challenge. Cooling centers traditionally operate during daytime hours when the worst heat is expected. A summer where nighttime lows fail to provide relief requires 24-hour cooling options. Some cities have begun pilot programs to keep certain public buildings open through the night during heat waves. The programs are expensive and politically controversial. They are also increasingly necessary. For agriculture, overnight warmth has its own consequences. Many crops, including corn and soybeans, depend on cool nights for proper grain filling. When overnight temperatures stay too high, yields drop. Cattle in feedlots experience continuous heat stress without the relief of nighttime cooldowns. Productivity drops. Mortality climbs. For energy systems, overnight warmth means that air conditioners run continuously through the night. Power demand, which used to drop sharply in the evening hours, now stays elevated. The infrastructure stress that used to peak in the afternoon now persists for 16 or 18 hours a day. The grid never gets a break. The cumulative effect is a summer that runs hotter, longer, and more relentlessly than the summers of memory. Older Americans who remember the summers of their youth are not imagining the difference. The data confirms it. The rhythm has changed. The dome of March 2026 was, in this sense, a preview of an August that had migrated into March, and the question many climate scientists were now privately asking was what August itself would feel like. The answer involved the next dome, the one that had not yet formed. In closed conferences and informal discussions, climate scientists studying heat extremes share a particular kind of conversation. It is not the conversation they have with reporters. It is the conversation they have with each other. The conversation is about the next dome. The previous 5 years have produced a string of record-shattering events. The 2020 Siberian heatwave, the 2021 Pacific Northwest dome, the 2022 European heat, the 2023 South American summer, the 2026 March dome over the western United States. The Southwest heatwave is solidly in the category of giant events, with temperatures up to 16.7 degrees Celsius above normal, says Stanford University climate scientist Chris Field. He lists 5 others in the last 6 years. 6 events in 6 years. Each one previously considered something that should occur every several centuries. The statistical implication is uncomfortable. Either the world is having an extraordinary run of bad luck, or the underlying probability distributions have shifted enough that these events are no longer rare. The math strongly favors the second explanation. A foundational study by Eric Fisher and colleagues in 2021 provided the theoretical framework that climate scientists keep returning to. In a warming climate, we should expect not just more frequent extremes, but record-shattering extremes, events that break previous records by much larger margins than historical experience would suggest. Record-shattering, not just record-breaking. The distinction matters. A record-breaking event nudges the previous mark by a small amount. Statisticians have understood this kind of event for centuries. The methods to estimate their frequency are well developed. They allow for orderly planning. A record-shattering event leaps past the previous mark by a margin that breaks the methods. The Pacific Northwest dome of 2021 shattered records by more than 5 degrees Celsius in some locations. The March dome of 2026 shattered them by similar margins. These are not statistical fluctuations, they are signals that the underlying system has changed. What scientists fear is that the record-shattering nature of recent events implies that the next dome could exceed the previous ones by similar margins. The Pacific Northwest dome killed hundreds. A future event that is several degrees hotter could kill thousands. A future event with similar geographic scope and just slightly different humidity conditions could push entire regions past human survivability thresholds. The geographic concern is particularly sharp. The March 2026 dome happened in the desert southwest, where dry air provided some protection. A similar atmospheric pattern over the Mississippi Valley in July, where the air is humid, would produce wet bulb temperatures that have not been seen in modern American history. Healthy people sitting in shade with unlimited water would face genuine risk. The other fear is duration. The March dome lasted roughly 2 weeks. A future event that locks in for 3 or 4 weeks, or even longer, becomes a different kind of disaster. Power grids that can survive a 2-week stress test cannot necessarily survive a 4-week one. Crops that can tolerate 2 weeks of extreme heat may fail completely after 3. Hospitals that can manage a surge of heat illness for 2 weeks may run out of capacity in longer events. There is also the question of compounding events. A dome that breaks the records in one region during one summer is one disaster. A dome followed by a hurricane, or by a derecho, or by a flooding event in another region becomes a cascading disaster. Federal emergency response capacity is finite. Insurance pools are finite. Mutual aid networks among cities and states are finite. A summer with multiple compound events strains every system simultaneously. Climate scientists studying the broader pattern keep coming back to a single observation. The atmosphere has more energy than it had a generation ago. The ocean has more heat than it had a generation ago. The water vapor content of the air is higher. The temperature contrasts between regions are shifting. The jet stream is wavier. The blocking patterns lock in more often. All of these factors point in the same direction: more extreme events, larger margins, more frequent occurrence. The probability distribution is sliding toward the dangerous tail. For the people responsible for keeping cities and citizens safe, the implication is a need to plan for events that have not yet been observed, to build infrastructure that can handle conditions that have not yet occurred, to develop response capabilities for disasters that have not yet happened. The dome of March 2026 was a preview. The question now is, what is being previewed? There is a moment in every long disaster when the people involved realize they are no longer waiting for something to happen. They realize it has already happened. The line has already been crossed. The question is no longer how to prevent it. The question is what to do now. For the United States and its relationship with extreme heat, that moment may have arrived in March 2026. The dome did things that were supposed to be impossible. Events as warm as in March 2026 would have been virtually impossible without human-induced climate change. Virtually impossible, mathematically unallowed. And yet, the event happened. For 2 weeks, across 30% of the country, setting more than 7,000 records, with climate signals at maximum intensity across the entire western half of the nation. What was once impossible is now actual, and the actual events of recent years have been clustering closer together. 5 record-shattering domes in 5 years, a pattern that in a stable climate should take centuries to produce. The line has been crossed. What comes after the line is harder to predict, but several broad themes are emerging from the work of climate scientists, urban planners, public health experts, and emergency managers. First, adaptation will become unavoidable. The decades of debate about whether to focus on mitigation or adaptation are effectively over. Mitigation, the long-term work of reducing greenhouse gas emissions, remains essential. But adaptation, the work of preparing for the warming that has already been baked in, is now urgent in a way it was not before. Cities, will need cooling infrastructure they have never built. Power grids will need redundancy they have never had. Building codes will need updates they have not received. Insurance systems will need restructuring they have resisted. Second, the geography of risk will continue to redistribute. Places that were comfortable for centuries may become uncomfortable. Places that were uncomfortable may become uninhabitable. Migration patterns will respond. Housing markets will respond. Politics will respond. The question of where Americans live and how is being quietly rewritten by the atmosphere. Third, the social fabric will face new tests. Heat events disproportionately affect the most vulnerable. Elderly residents in cities without air conditioning, low-income workers in outdoor jobs, people with disabilities or chronic illnesses, communities that already lack the resources to prepare. The choices a society makes about how to protect these populations will define the kind of country it becomes. Fourth, the relationship between weather and identity will shift. Cities that built their brands around their climate, such as Phoenix as the desert paradise, Denver as the mile-high winter destination, Seattle as the cool, green corner of the country, will need to renegotiate their relationship with their environments. The climate that built them is no longer the climate they exist in. The next generation of residents will know a different version of these places. Fifth, the global picture will continue to matter. The United States is one country in one warming planet. Heat domes in North America are connected through the great atmospheric circulation to events in Europe, Asia, and the Southern Hemisphere. The international climate negotiations that have stretched across decades are no longer abstract. They are determining the shape of summers that have not yet arrived. For the individual, the practical question is how to live well under these conditions. The answer is not despair. It is preparation, attention, and engagement. Knowing your local risks, building social networks that can check on neighbors, supporting policies that update infrastructure for the climate that exists, voting for leaders who take the problem seriously, reducing personal emissions where possible, pressing institutions to do the same. The dome of March 2026 will be remembered for many things: the records it broke, the snow it melted, the reservoirs it stressed, the grids it strained, the communities it scared, the questions it raised. It will also be remembered for what it revealed: that the playbook has been thrown out, that the assumptions of the past century are no longer reliable, that the climate Americans inherited from their grandparents is no longer the climate they will pass to their grandchildren. The atmosphere is doing what physics dictates. The physics just hits different on a warmer planet. What comes next depends on what is done now. The dome was a question. The answer is still being written.